Good afternoon, everybody, or evening, or morning, depending on when you're watching this. Anyway, we're going to talk about several algebra topics that I think are going to be useful in the not too distant future. The first of which is simplifying radicals, or square roots. So, when you're simplifying a square root, you want to rewrite it either as a whole number or so that you have the smallest number possible underneath the radical. That's this funny looking symbol thing right here. Now, that's a pretty easy process if the number that is underneath the square root bar is a perfect square. So, like with this, when I see this number, I think, what is the number that you multiply by itself to get 9? Okay, well, and that, of course, is 3, right? 3 times 3 makes 9. So the square root of 9 is 3. Well, what's the square root of 16? What number do you multiply by itself to get 16? That is, of course, 4. And so we're done there. And one more time, the square root of 25, well, that's 5, because 5 times 5 makes 25. So if the number underneath the radical is a square root, it's really easy to simplify. However, you might also run into some problems like this. And for these, I'm fairly certain that there's no number you can multiply by itself to get 18, not a whole number anyway. But I do know that 18 is the same thing as 9 times 2, right? Okay. And one of those numbers is a perfect square. It's 9, right? So the square root of 18 is the same thing as the square root of 9 times the square root of 2. And we just talked about what the square root of 9 is. It's the regular number 3. So if you can find one of the factors of your given number as a perfect square, then you can rewrite it something like this. I'm going to do the same thing with 60. 60. What multiplies to make 60? Let me think here. Oh, I remember now. It's 4 and 15. Okay. 4 is a perfect square as well, and so you can rewrite that as 2 times the square root of 15. And even though 15 is kind of a bigger number, there's no perfect squares in its factors. It's just 5 times 3, so that can't be any more simplified than it is right now. Okay, mission accomplished. Next topic, the distributive property. So, sometimes it's useful to know how to distribute. So here we go. You might remember that when you have a number on the outside of the parentheses, you multiply it by both of the numbers on the inside. So this 4 on the outside gets multiplied by 5x. That would become 20x. And 4 times 7 is 28. And we've distributed. And I can't put together 20x with 28 because one of them has an x, the other one doesn't. They're not like terms. When you have something like this, though, when there's two binomials next to each other, well, then you have to take each member of the first group and multiply by each member of the second group. And here's what I mean by that. So first I take x times x. We know that that's x squared. Then I also take x times 5, and that's 5x. Okay, so I took x times both of the things in the second group. Now I do the same thing with the 6. 6 times x becomes 6x. And then at the end, 6 times 5, well, that's 30. And in most of these problems, you can usually simplify something after that. Here there are a couple of like terms, 5x and 6x. Those can be put together. And so we would end up x squared plus 11x plus 30 as our final simplified version of that. Or expanded version might be a more accurate way to put it. Let's try that one more time. X minus 7 times x plus 2. I take x times x, that's x squared. Then I take x times 2, that's 2x. Then I do negative 7 times x, that's negative 7x. And lastly, I take negative 7 times 2, and that's negative 14. When the dust settles, I've got a couple of like terms here. These ones in the middle both have an x with them, 2x and negative 7x. And so our final answer there, x squared minus 5x minus 14. Notice that I can't put together the x squared with the regular 5x. This one has a different exponent, so they're not like terms. They can't go together. Closely related to the concept of the distributive property is factoring, especially factoring quadratics, which is basically the exact opposite of what we're doing right here. So here we started with two binomials and we ended up expanding it out to this expression down here in expanded form. Here we're going to go the opposite direction. We want to end up back at two parenthesis things, two binomials. Okay, so to do that, I need to think about specifically numbers that multiply to make the number on the end, but add or subtract to make the number in the middle. Okay, what multiplies to make 20? Well, that's 1 and 20, or 2 and 10, or 4 and 5. Now, all of those things multiply to make 20, but only one of them also adds up to make 12. Which one is it? Well, that's, of course, 2 and 10. Okay, 1 plus 20 is 21, 4 plus 5 is 9, but 2 plus 10 makes 12, which is what we were looking for. Numbers that multiply to make 20, but add up to 12. And so the factored version of this would be x plus 2 times x plus 10. If you want to double check my work, you can expand it using the methods we talked about on the previous page. Okay. The second one, I'm looking for numbers that multiply to make negative 24, but add or subtract to make negative 5. Okay. So what makes 24? There's 1 and 24, or 2 and 12. 24 has a lot of factors. 3 and 8, or 4 and 6. Now, if you want to think about this for a second, which of those pair of numbers could add or subtract to make negative 5? If you took a moment to think about it, hopefully you notice that it is 8 and 3. Now, for that to work out, though, one of them has to be a negative number, and which one is it? Well, since this is negative 5, I know that it's 8. 3 minus 8 would give me negative 5. And then when you multiply them, 3 times negative 8, that gives you negative 24. Okay. Once more with feeling, this last one, what multiplies to make the number on the end 40, but adds or subtracts to make 6 in the middle? I'm going to think about the factors 40. I think you should too. Maybe you could do this one without me if you took a moment to pause and try it yourself. And I've written them all out. Well, that's everything. Which of those pairs of numbers that multiply to make 40 also can add or subtract to make 6 the number in the middle? It's, of course, the last set, 4 and 10. Now here, again, if I added those, that would make 14. I need to subtract one of them to end up at 6, and that's got to be the 4 in this case. So our final answer would be something like this: x plus 10 times x minus 4.